All right, so we're going to look at how to build maximum likelihood functions and then how to solve for the maximum likelihood estimate for our missing parameters. So typically, you will see these referred to as maximum likelihood functions as MLF. So that's just the function that we solve for, that we build in order to construct our maximum likelihood estimate, which is the MLE in abbreviation form. So we may encounter these as we go through this discussion. The maximum likelihood function is essentially the product of a series of outcomes. We express the probability of a particular outcome using a distribution with a particular unknown parameter, and then we multiply the outcomes that we get with the observation value filled in, but the parameter still unknown. So typically when we're solving for probability distributions, we know the parameter and we're estimating with to find the X value that satisfies a particular condition. This is the reverse scenario. We have the observations that we've gotten from data, the X's, and what we don't know is the parameter lambda. So sometimes you'll see this notation where the probability distribution is designated as F, and we have the likelihood distribution for that probability function designated as L of F. And then what it's really constructed in terms of is it's going to be a function of the missing parameter or parameters. And again, it's built from this capital Pi indicates a product. We're multiplying the probability distribution with our observation values filled in, and then our unknown lambda. Again, we could call it lambda in our particular example, or this is a stand-in for any parameter that we happen to be using. And then again, these X values are filled in, and so sometimes you'll just see it as F sub I of lambda instead of F of X sub I comma lambda. All right, so I wanted to go through two examples of discrete cases, of cases where there's one lambda to be solved for. And then we will look at, in another video, some examples where you have to solve for these problems numerically, not with calculus. And another example in another video where we'll look at one where we have to use multivariable calculus in order to find them. But so in this video, we're just going to look at examples where we have things that are one variable that we have to solve for one parameter. And so we can just use one variable calculus to do the calculations. All right, so here we're going to look at a continuous distribution, the exponential distribution, for time between events in a Poisson process. Now, the Poisson process would often be set up quite similarly to this, just as a note, but it would actually be more similar to the numerical calculation we have to do in this next video, the one after this, because it has a factorial in that formula, and so we can't take the derivative of a factorial directly. So here we're again exponential distribution. We have these outcomes. We've watched the time between processes, and I've made them integers here just to make the math a little easier. In a real world typical example, of course, you would be measuring in with decimals and things like that. But the math itself doesn't change. It just the number of things you have to keep track of. So we have this series of observations. We want to find out, we think it's an exponential distribution. We want to find out what the parameter lambda for our exponential distribution is that is most likely to fit this data, given the information we have. So our first observation comes from an exponential distribution where the outcome X was 5. And our second observation being 2, so we plug that in our second function has, again, some unknown parameter lambda, but the x turned out to be 2. And so we substitute that in. And so each one of these observations that we have get plugged into our exponential distribution with the x value known. And so I've gone through and I've listed here all of those different observations and how they, that exponential distribution is processed with a known x. The maximum likelihood function is the product of these. So remember, we're thinking of this as a probability outcome, but it's a probability outcome that had a particular x value involved in it. And so our maximum likelihood function, the function that we're constructing, is the event where all of these things happen simultaneously or in succession, but they all have to be true. And so we're going to feed all of that data, and we're going to make our function by making a product of all of these individual probability distributions with our individual observations. And then when we simplify this expression, notice each one of these expressions has a lambda out front. There were 10 observations, so that's lambda to the 10. And then when we multiply exponential functions, we add the exponents. And so when you add up all of these observations, you end up with 30. And so these are all negative in the probability distribution. So you end up with negative 30 lambda. And so this is our maximum likelihood function. So again, this is sort of the general form, the product of our exponential distributions with our x sub i's. Again, in the abstract, if you do this for n calculations, you get lambda to the n, and then the lambda in your exponent, the coefficient of that, the product in the exponential exponent, it turns into a sum. And so this becomes the sum of all of those x sub I. So again, this is the specific case. This is the abstract case for dealing with an exponential distribution. Now, if we want to then find the value of lambda, that is the maximum likelihood, the most likely outcome for this, we would take the derivative of this function and set it equal to 0. You can also do this algebraically, graphically, of course. You could plot it and try to find the maximum. In the case of the Poisson distribution, for instance, that's what you would have to do, because you can evaluate factorials at different values and then figure out what the maximum has to be, but you can't take the derivative of x factorial or lambda factorial or whatever your parameter is. But in this scenario, this is a nice continuous function. We can easily take the derivative of it. The maximum will occur when the derivative is 0. You can get minimums. So sometimes when you do these problems, you will get lambda equals a parameter equals 0. That's clearly not a maximum. Or you may get, again, depending on what kind of distribution it is, you may get a parameter equal to 1, which again might also not be a maximum. You have to think about what the parameter means. In this case, this is lambda is a mean time to the event, so it is it has to be positive. 0 would not make any sense. And what you would basically then do is you would do your derivative. You would need a product rule to do this derivative, but then you would set it equal to 0 and then do some algebra to get your lambda value. Now, what I want to look at is another problem where we set things up. And in this case, we're going to look at the binomial and negative binomial distributions. They're going to basically behave pretty much the same way. When you have a fixed set of outcomes, you can't actually tell whether it came from a negative binomial or a binomial distribution, because once you get to that final outcome, you quit, right? So in a negative binomial distribution, you allow for the possibility that you could be like doing your coin flips forever. there's an increasingly unlikely scenario where you could literally never get another outcome. Whereas in the binomial distribution, you're saying this is how many outcomes you've had in this many flips. By the time when you finally get that last flip, your negative binomial will already basically be, okay, I needed this many flips in order to get this many heads. So they end up actually looking the same in the case of the maximum likelihood function scenario. So we have a Bernoulli random variable, and if we choose in advance to take 30 samples, we are again saying that's a binomial distribution. If we simply we ended up with 30 samples after trying to get 10 heads, then this would also be a scenario where, okay, so it took us 30 times to get 10 heads, fine. Then that would just be our number of trials that we use, but that would be a fixed value by the time we're doing this calculation. So let's suppose we did our flips and we ended up with this string of outcomes, 10 heads and 20 tails. Now, we don't have to worry about the coefficient that's out front. Coefficients are not going to change the likelihood of whether we are doing a zero or not. Whether we have a zero, multiplying a zero by a number doesn't change anything at all. If we're doing this outcome by outcome, so if, again, let's go back and look at our string. So in our first scenario, we got a head. And so the probability for heads is 1 minus p. And then each time we have a probability for tails, we multiply by p. Again, depending on which thing you're solving for, what's the probability of heads, probability of tails, you could flip these as long as you're consistent with what you're designating to be what. It won't make any difference. But we started out with a head. And so when we set up our string of values, we set up a 1 minus p, since we said that was the probability for heads. There's one copy of that. And then we had 2 tails in a row. And so in our formula, we wrote down probability for tails was p. We had 2 of them, so that's p squared. Again, go back and look at our string. We then had 2 heads and so forth. And so we're converting our outcomes of heads or tails into strings of either 1 minus p every time there's a head, or p every time there's a tail. And if there's copies of them, we can shorten this by using exponents. So 1 head, 2 tails, 2 heads, 3 tails, 1 head, 1 tail, 1 head, 4 tails, 1 head, 1 tail, 1 head, 1 tail, 2 heads, 5 tails, 1 head, 3 tails. And that's our 30 outcomes. And again, if you multiply this together, what you end up with is p to the 20 and 1 minus p to the 10, which looks, again, an awful lot like our binomial and negative binomial distributions, except without the coefficients. Now, sometimes I've seen this example done in textbooks, and sometimes it's the only example that they do in some textbooks. And I think it's really deceptive to stop with this example because it is basically just pulling in the binomial formula and pulling in the negative binomial formula and dumping out the coefficients. But as we saw with the exponential example, that doesn't work in most cases. It just happens to work here because these are already collections of multiple events. But we found our function, P20, 1 minus P to the 10. And then again, if we wanted to find our maximum likelihood estimate, all that's required here is one variable calculus. We would take the derivative, set it equal to 0. And then again, in this problem, you're going to get P equals 0 and P equals 1 as possibilities. Those are both minimum. minima values. They're the least likely outcomes. And then you'll get a third value that will actually be the maximum.